Greetings, space cadets of knowledge. I'm Ernis, your guide through the fascinating, sometimes bewildering, landscape of academic research. Today, we're strapping in for a deep dive into a paper that tackles a major bottleneck in how we build and use large language models. The paper is Optimal Inference Schedules for Masked Diffusion Models by Chen, Cong and Li. Now, I know what you might be thinking. Masked diffusion models? Inference schedules? Sounds like a recipe for a quantum headache, but fear not. We're going to break this down, Feynman style, into bite-sized pieces that even a slightly soused Rick Sanchez could maybe appreciate. The problem: standard auto-regressive language models, like those that predict the next word in a sentence, are inherently slow. They have to generate words one after another, in sequence. Imagine a cosmic assembly line, where each station can only process one piece at a time. It is a major bottleneck for scaling AI systems. The proposed solution? Masked diffusion models, or MDMs. Think of MDMs as linguistic ninjas, capable of sampling many words at once, out of order, in parallel. It is a revolutionary technique where you mask parts of the sentence and let the model fill in the blanks. It's like having a team of cosmic painters, each working on a different section of the canvas simultaneously. Now, the big question the paper addresses is, how much parallel sampling can these MDMs actually handle before their performance starts to degrade? Can we just crank up the parallelization to 11 and expect everything to be sunshine and rainbows? Or is there a limit? To understand this, let's build a mental memory palace. Picture a vast, shimmering city made of data. Each building represents a different concept in this paper. Our first stop, the information curve. This concept is critical to understanding the paper, but it's tough to grasp. Think of it as a map of dependencies within the data. Each point on the curve shows the average amount of information that one word in a sentence shares with all the other words around it. Now, for this paper, we're going to name it Z-curve, for simplicity. Imagine this curve is the blueprint for a super efficient postal service in our cosmic city. If Z-curve is smooth and gentle, it means words are highly interconnected, and we need a carefully orchestrated delivery schedule. But if Z-curve is jagged and erratic, it means words are more independent, and we can just yeet packages at random with minimal loss of performance. The authors discovered an exact characterization of the optimal unmasking schedule for any data distribution. It exposes an elegant connection to univariate function approximation. The authors give a new, exact characterization of the expected divergence between the true distribution and the sampled distribution, for any distribution and any unmasking schedule for the sampler, showing an elegant connection to the theory of univariate function approximation. The first key result, theorem: the optimal unmasking schedule is directly related to how well you can approximate Z-curve. If you can closely approximate Z-curve with a few simple steps, you can sample efficiently. If Z-curve is complex and wiggly, you're going to need more steps, more sequential processing. The best unmasking schedule is given by the best step approximation. Our next stop in the memory palace: the impossibility results. This is where things get a little, well, Rick-esque. Turns out, even if you know the shape of Z-curve, figuring out the optimal unmasking schedule is surprisingly difficult. Imagine you are looking at a cosmic Rorschach blot, and knowing that the optimal schedule can be found. The authors prove that there isn't a single algorithm that can simultaneously achieve good performance across all possible data distributions. It's like trying to build a universal translator that works for every language in the multiverse. Some languages are just too alien. Fine, yeah, I guess. They show that even knowing the distribution, there isn't a single sampling algorithm which achieves iteration complexity. Look, the point is, this paper is a big deal. Now, this might sound depressing, but don't lose hope. The authors don't just leave us in a pit of despair. They offer a glimmer of light in the form of total correlation and dual total correlation. Think of these as overall measures of dependency within the data. Total correlation tells you how much the words in a sentence deviate from being completely independent. Dual total correlation, on the other hand, tells you how much each word depends on all the other words taken together. The third key result? It is the dual total correlation and reduction to a single hyperparameter sweep. It shows that for any distribution, there exist unmasking schedules depending only on a single scalar parameter quantifying correlations in the distribution which achieve small expected KL error. It turns out that with access to these correlations, one can sample in steps without any visible loss in performance. The authors demonstrate that even without knowing the full shape of Z-curve, you can still design efficient unmasking schedules by focusing on these global measures of dependency. It's like navigating our cosmic city with a compass and a rough map, instead of trying to memorize every single street. What does all this mean for the future of language models? Well, it suggests that MDMs are a promising path towards faster, more scalable AI. But it also highlights the importance of understanding the underlying structure of the data. We can't just blindly throw more computing power at the problem. We need to be clever about how we parallelize the sampling process. In essence, this paper is a call to arms for researchers to develop better tools for analyzing and exploiting the dependencies within language data. It's a reminder that even in the age of deep learning, there's still plenty of room for elegant theory and insightful analysis. So, go forth, bright explorers. Delve into the depths of masked diffusion models, unravel the mysteries of Z-curve, and remember, even if things get a little Rick-ish, there's always a glimmer of Sagan-esque wonder to be found in the pursuit of knowledge. Until next time.